Welcome to the second video of week 5 of this introductory course on synchrotrons and X-ray free electron lasers. Now in this video we will familiarise ourselves with monochromators and the handling of harmonic signal. What are monochromators and why do we need them? Monochromators, often called monos for short, select a certain bandwidth or set of bandwidths of frequencies from synchrotron radiation sources. Bending magnets and wigglers provide very broadband radiation, and for the large majority of experiments, only a small fraction of this, in the form of a narrow range of energies, is used. Even the bandwidths of undulator spectral peaks, as they emerge, is more often than not insufficient for many types of experiments and require further monochromatization. For example, X-ray absorption spectra contain subtle features that can provide invaluable chemical and orientational information. The pre-peak in the Zane's spectrum of copper at its K absorption edge is highlighted here with an asterisk, and it provides information on the oxidation state. The width of this peak is approximately 1.7 electron volts. In other words, approximately 1/500th of its energy. In order to resolve such features, the spectral bandwidth delta nu divided by nu must be better than this. On the right-hand side, a typical macromolecular diffraction pattern is shown. If we blow up a portion of this, we see that diffraction spots are only very slightly angularly separated and would overlap if the degree of monochromacity were an order of magnitude worse. Depending on the photon energy range of the beamline and the demands for flux, different monochromator types are used. Soft X-ray beamlines use gratings, while most hard X-ray beamlines employ monos based on crystal diffraction. The tender X-ray regime is also mostly served by crystal monochromators, though they can use so-called multilayer monochromators as well. Multilayer monos are also employed fairly extensively in the medium hard X-ray regime as a means to obtain more flux through their intrinsically larger bandwidths. A selection of different but representative monochromator types from synchrotrons around the world is shown here as a function of photon energy and periodic spacing d. One sees immediately the strong correlation between photon energy and d spacing. This should come as no surprise. A high photon energy is associated with short wavelengths, for which one needs a diffraction element of similar periodic dimensions. How do grating and crystal monochromators differ from each other? Gratings can come in various flavors regarding their groove profiles, of which 3 examples are shown here. Gratings are typically fabricated via advanced lithographic and etching techniques on glass substrates. Scattering of grating features leads, at certain angles, to constructive interference when the optical path difference, d sine theta I minus sine theta r, is equal to an integer number of wavelengths. As we saw in the previous slide, typical grating periodicities are anywhere between a couple of 100 nanometers to a few microns. In the case of a crystal, for which d is a few angstroms, interference of hard X-rays is between successive layers of atomic planes perpendicular to the scattering vector, which therefore follows the famous Bragg law. How is the performance of grating monochromators affected by the number of illuminated facets, N, F? To understand this better, we resort to the use of Argand diagrams once again. We assume that illumination of each facet is the same, and that therefore the scattering amplitude is the same. But how these scattered wavelets add up depend on their relative phase, in other words, how they interfere with each other. Let's consider first the case of illumination of just 4 facets. If the optical path difference between scattering of adjacent facets is an integer multiple of wavelengths, the phase difference will be an integer multiple of 2 pi, and the scattering amplitudes will all add up in one direction to produce a total amplitude 4 times the length of the individual scattering amplitudes from one facet. Now, let us change the incident and/or exit angle so that the phase difference between adjacent facets is pi upon 12 or 15 degrees. The vector addition of the 4 contributions will begin to curl round on itself and the total amplitude will decrease, shown by this second yellow arrow here. We see this is still more pronounced for a phase difference of pi upon 6, or 30 degrees, now shown here with this third yellow arrow. Indeed, at a phase difference of 90 degrees, or pi upon 2, the vectors will form 4 sides of a square and cancel each other out entirely, shown here. At pi and 3 pi upon 2, the same complete destructive interference will occur until, after a shift in phase of 2 pi, a maximum is again reached. Now, using the same arguments, a similar situation arises when 8 facets are illuminated. But now, for a given phase difference, the degree of destructive interference increases more rapidly as one moves away from a phase difference of 2 pi, or an integer number of wavelengths. As more individual scattering amplitudes are involved, and the vector addition curls round on itself more. The position and size of the total amplitude as a function of phase difference between 0 and 2 pi is shown in the animation in the center for 8 facets. The result is that the condition for constructive interference becomes stricter and consequently the interference maxima become narrower. Indeed, it can be shown that the relative bandwidth lambda divided by delta lambda is directly proportional to the number of illuminated facets, NF. In modern soft X-ray monochromators, NF can easily be several thousand, and bandwidths comparable and often superior to those demonstrated by crystals such as silicon can be achieved. As was briefly mentioned in the first video of this week, it's possible to bend dispersive elements such as gratings in order to simultaneously disperse the radiation, in other words to monochromatize, and to focus it at the same time. In spherical grating monochromators, or SGMs, the grating surface has a concave spherical form with a radius RB. The grating grooves, or lines, are perpendicular to the so-called Rowland circle, which lies tangential to the center of the grating and has a radius RR, which is half that of the spherical grating radius. Any source lying somewhere on the Rowland circle will select a certain wavelength and refocus it at another position on that Rowland circle. Different energies can be selected by moving the source around the Rowland circle, as shown here. Crystal monochromators use single crystals to select a given energy using Bragg diffraction. The most common crystal material is silicon. Silicon has a reasonable thermal conductivity and can be efficiently cooled by liquid nitrogen in order to minimize the mechanical strain induced by a local thermal bump where the incoming polychromatic beam impinges on the crystal surface. Importantly, silicon can be produced as a near-perfect single crystal with linear dimensions up to tens of centimeters, thanks to its ubiquitous use in the semiconductor industry, where large and exceedingly perfect wafers are produced en masse. The most common crystallographic orientation is the 111. Bragg's law predicts that if one were to have a perfect, non-absorbing, and very weakly scattering crystal of infinite depth and a perfectly collimated incoming polychromatic beam, the bandwidth of the selected radiation would actually be infinitely narrow. However, there is always some residual beam divergence, slightly misaligned crystallites making up the imperfect single crystal. This is referred to as mosaicity, and finite absorption and extinction depths. These all contribute to a given crystal always selecting a bandwidth delta lambda, which is greater than 0. In the case of silicon, the contribution that normally dominates is due to the finite extinction depth, resulting in a so-called Darwin width of the Bragg reflection, which results in a relative spectral bandwidth a little larger than 10 to the minus 4. Hence, 1 angstrom radiation with an energy of 12.398 kiloelectron volts has a minimum bandwidth of approximately 1.7 electron volts. Note that the corresponding width in theta, the Bragg angle, is delta lambda divided by lambda multiplied by the tangent of theta, and thus the crystal also accepts a fine angular range of the order of 1/1000th of a degree. This leads us to the concept of dispersive or non-dispersive configurations in monochromators. We've already argued that the incoming radiation is polychromatic and divergent to a certain degree, and that the crystal thus selects a band of wavelengths from this incoming beam. We would therefore expect a range of photon energies to be reflected off the crystal, the lower energy photons being selected at steeper angles and those with higher energy at shallower angles, according to Bragg's law, and shown here. These will be reflected specularly with respect to the diffracting planes. If we now place an identical crystal in the path of the reflected rays, we can adjust its orientation so that all of those wavelengths which were selected by the first crystal are preserved after reflection of the second crystal. This is because they impinge at the same angles. This is called the non-dispersive configuration. Now let's consider an alternative setup. We're going to concentrate now with the central energy shown here in green. In the previous slide, this was intercepted by the second crystal and reflected back parallel to its initial direction. But we could also reflect the beam in the opposite sense, shown here. Now, what about the other two energies? There's of course a band of energies, we're just showing 3 representative ones. In this new setup, these no longer impinge on the surface of the second crystal at the same relative angle as on the first crystal, as we see here. And as a result, they will be lost or strongly attenuated. This is called a dispersive setup, as a narrower range of wavelengths is selected by the second crystal than by the first. This configuration is therefore more monochromatic, but at the cost of flux. A similar effect can be achieved by using a different crystal type or crystal orientation for the second element. This is succinctly explained using so-called Dumont diagrams, for which I direct you to the reference given here. There are different types of crystal monochromators. A common configuration is the double crystal monochromator, or DCM, which uses two identical crystals in the non-dispersive mode. This not only provides greater flux, but also allows the beam to emerge from the monochromator parallel to the incident beam. If the offset in the monochromatized beam is to remain constant for all photon energies, not only do both crystals have to rotate to the Bragg angle, but also one of them, in this figure, the second, must be translated along the direction of the beam axis. Channel cut monochromators are fabricated using just one single crystal, which has had a central channel milled out of it. This adds simplicity and speed to changing the photon energy, requiring a single rotation stage, a definite advantage when performing rapid energy scans in certain types of spectroscopic experiments, where physical and/or chemical changes are to be followed rapidly, with as many as 40 energy scans per second in modern beamlines. The disadvantage is that the exit beam's height will change as the CCM is rotated, though this can be made to be minimal by making the channel width, big D, to be as small as possible and the scanning over a not too large range of photon energies, which in turn determines the angular range of theta. Lastly, the problem of having a varying exit beam in a CCM can be overcome by using a 4-bounce configuration shown here on the right. This consists essentially of a mirror image of two CCMs. Here, the disadvantage is that this is a dispersive setup associated with a certain loss in flux. Finally, we discuss multilayer monochromators. Crystals diffract X-rays through scattering planes of atoms. It's a three-dimensional system, exploiting the periodicity in the direction parallel to the scattering vector. In the case of multilayers, scattering is produced by a contrast in electron density at the interfaces between heavy reflection layers and lighter spacer layers. The only required periodicity is in one direction. Indeed, in many instances, on an atomic level, the materials which make up the reflection and spacer layers may be amorphous, with no periodicity at this spatial scale of angstroms. What motivates a beamline scientist to use a multilayer monochromator? First, the reflectivity can be very high. This, coupled with a bandwidth, which may typically be 100 times larger than that provided by single crystals, means that the flux output from monochromators using multilayers can be very high. Techniques such as X-ray computed tomography profit from this, as in few cases does a narrow bandwidth bring advantages, while rapid data acquisition can access morphological changes on the sub-second or even the few millisecond timescale. Lastly, we will also see that the larger periodicity of multilayers compared to crystals by an order of magnitude can lead to refraction effects that can be exploited in suppressing harmonic contamination. There are several design parameters which determine the performance of a multilayer monochromator. We have already mentioned that one requires heavy reflecting layers made of heavier elements such as ruthenium or tungsten, separated by low Z spacer layers made of, for example, boron or carbon or a combination of these. The strength of the reflection is determined partly by the ratio of thicknesses of the thick to thin layer. Two thick layers means that the X-rays can't penetrate deep enough into the multilayer, while two thin layers reduces the reflected intensity. A common ratio of thicknesses is 0.4 to 0.6 heavy to light, though this can vary depending on the applications. The total periodicity, big lambda, is typically measured in a few nanometers, while the number of layers is commonly of the order of about 100. The total thickness of the multilayer structure is equal to n lambda. If one makes this too large, this means that the X-rays can't penetrate to the bottom of the structure, obviating any advantages in adding all the extra layers. Lastly, the layers should have atomically smooth interfaces in order to perform properly. The wavelengths that are selected are approximately given by the equation shown here. That is, small lambda, the photon wavelength, is equal to 2 times big lambda, the multilayer periodicity, divided by m, the order of the reflection, times sine theta. This is in essence identical to the Bragg equation used for crystals. An example of a multilayer installed at the ESRF BM5 beamline is shown here. The reflectivity at an incident angle of 1.15 degrees is shown on the right. Because the reflection and spacer layers are of equal thickness, all even harmonic reflections are suppressed. This phenomenon is called a systematic absence. It's outside the remit of this course, but it is an important feature of crystallography. The first harmonic is at 8.01 kiloelectron volts, shown here. The third harmonic, however, is not at 3 times this value, that is 24.03 kiloelectron volts, as we might have expected from our equation shown in the previous slide, but instead it is in fact at 23.27 kiloelectron volts, which is 760 electron volts lower in energy. The reason for this, as I just mentioned, the previous equation is in fact just an approximation. The exact equation is shown here. Now, the second correction term in the brackets, k lambda squared divided by m squared, accounts for refraction effects. One might ask why this is not also employed in the normal Bragg equation for crystals. First of all, in some cases requiring the highest accuracy, it actually is. However, the deviations are much smaller, and this is due to the fact that the wavelengths being selected in multilayers are very much smaller than the periodicity, resulting in shallow angles and a larger refractive effect. In other words, a larger change in angle of the X-rays as they cross the interface between spacer and reflecting layer. This phenomenon means that multilayers can be used to suppress higher harmonics. This brings us to the last topic of this video, that of harmonic suppression strategies. In most experiments, we would like to suppress integer multiples of the photon energy of interest, though, because both the undulator and the monochromator harmonics are spaced evenly in energy, this cannot be done by normal monochromatization alone, though we have mentioned already that it's possible using multilayers. So we have the mono, and we just narrow everything down, even for the case of undulators. Although we have seen how this can be done using a multilayer, suppression of these harmonics, and also in the last video by one or more reflections off mirrors, are there any other possibilities we could use? Well, there are. One simple approach is to use crystals which suppress certain higher energies because the associated reflections are forbidden. This again is called a systematic absence. For example, for reasons of symmetry within the unit cell, the reflections highlighted in red for silicon 111 and silicon 001 crystals are all nominally forbidden. Now I say nominally as their complete suppression assumes that the electron cloud surrounding each atom has a perfectly spherical symmetry, which we know not to be 100% valid. For example, the electrons associated with covalent bonding are far from spherically distributed. Hence, these reflections tend to be very weak but aren't entirely absent. Another approach is to slightly detune the monochromator. Now, the width, actually the Darwin width of each reflection in the family M times HKL, so for example, the 111, the 222, the 333, the 444, etc., reflections of silicon, is given by WD is equal to K divided by M squared multiplied by F, the structure factor for that particular reflection. Now F falls off with increasing M. Hence the Darwin width gets rapidly narrower with M. So only a moderate detuning and a modest loss of flux of the monochromator at the fundamental with M equals 1 will mean that the higher harmonics are much more detuned. Monochromators are the heart of X-ray optics. This video has been devoted to their description. We have now covered the generation of synchrotron light over the previous 2 weeks, and its filtering, focusing and monochromatization in the first 2 videos of this week. We complete this week's videos in the 3rd installment by discussing X-ray detectors.